Now 10.3 is on polar coordinate system. And for today, I would like to do the following. Uh, First one is the region in polar, and then second, common graphs, common equations, and common graph. And then after that, we'll talk about distance between points. And then we will do, what's that? Tangent line. Maybe to be more precise, horizontal tangent line and then vertical tangent line. Okay, so there's a chance that we actually spend a long time here and we just be able to touch base 10.4 a little bit later on. Last time we have done converting. So the one we did last time was convert from polar to rectangular, vice versa. Now we will see inequality in polar coordinate system, which then will represent some region. Actually, I would prefer to deal with common equation first. But anyway, region in polar, for example, I think at the same time, I will talk about the equation then. Okay, so for example, when we say R equals to 2, what does it mean? This means distance from origin is 2. All the coordinates whose distance from origin is 2 should give us a circle with radius 2. Okay, the picture should look like that, right? Okay, now then how do we show the equation from polar equation into rectangular equation? And R equals to 2, so R squared equals to 2 squared, which is 4. But R squared in rectangular is x squared plus y squared equals to 4. So it actually confirms that R equals to 2 in polar represents a circle with radius 2 in rectangular. Now then, how do we get into region in polar if we have inequality? So if I extend further to inequality, for example, when we have R is less than equal to 2, all the coordinates whose distance from origin is at most 2. That gives us not only a circle, but also everything in the interior, including the boundary. Okay, including the boundary. Now, if we don't include 2 less than, strictly less than 2, then it will be a circle. Okay, let me draw it this way. But on the boundary, I use dashes instead to say that it's not including the boundary. Okay, to say that it's not including the boundary, then I use dashes on the boundary and I shade inside. Now, if I make the R greater than 2, for example, then you shade outside of that circle instead. Okay, so actually for us to do the region, we need to deal with the boundary first. Okay. Second, what happens if we have, for example, the theta is the one equals to a constant. Let's say theta equals to pi over 4 in polar. Theta equals to pi over 4 represent actually a line 45 degrees. Okay, this is pi over 4 here. But actually, that's if you assume the radius cannot be negative. But the ambiguity is the radius can be negative. Okay, the radius can be negative. So these all the coordinates that we have here has positive radius. Okay, but the angle is pi over 4. Now what we have here have negative radius, but the angle is pi over 4. Okay, now in rectangular coordinate system, it's clearly y equals to x. Now, how do we show that though? How do we show that this polar equation here represent y equals to x? Now, we know tangent theta represent x, y over x. So I apply tangent to the theta, I get y over x, and tangent pi over 4 is 1. What we do here is actually something very, very important. If you took pre-calculus from me at WLAC College, then you see the following, that the slope of this line, the slope of any line, not only this line, the slope of any line, how do I get this? Oh, no, that's not the one I wanted. The slope of a line, so if I get a line here, no, that's not the one. I tried to do it fast, I end up messing up. Now, the slope of this line equals to the tangent of this theta. Okay, let me say it again. Tangent of the angle theta, angle from positive x-axis, is equals to the slope of the line. Okay, so let's say, for example, I change the question a little bit. Let's say I say theta equals to pi over 6. Then what is the equation in rectangular coordinate system correspond to that? That will be tangent theta equals to tangent pi over 6. Okay, tangent theta is y over x, and tangent pi over 6 is 1 over radical 3. So the equation of the line is y equals to x over radical 3. Now, on the other hand, if somebody asks this question, suppose I have these two lines. Let's say this one here. I make up equation y equals to 2x minus 1, and this one here, let's say x plus 2y equals to 3. And we are interested in finding the angle here. Let's call this angle theta. What is the angle between two lines? Now what you can do is you find the angle through the positive x-axis for the red line, right? Call this theta 1. And the angle from positive x-axis, you will see this is negative angle. This is theta 2. Okay, so theta 1 is tangent inverse of the slope 2, while theta 2 is tangent inverse of the slope negative 1/2. Right? This is y equals to negative 1/2 x plus 3/2. Okay, so angle theta must be theta 1 minus theta 2. That's tangent inverse of 2 minus tangent inverse of negative 1/2. That's tangent inverse of 2 plus tangent inverse of 1/2. Okay, that's actually the side effect of this polar observation. Now, so what about region? Suppose, for example, I see problems number 10. If I see problem number 10, can you sketch the region where the r is between 1 to 3 and the theta is between pi over 6 to 5 pi over 6, actually without cosine. So it must be between these two circles, right? Let's say this is the circle with radius 1. I do it without, not to scale. Okay, and this is the one with radius 3. This is 1, this is 3. Okay, and then the theta is between pi over 6, 30 degrees here, to 5 pi over 6, 150 degrees. This is for theta equals to pi over 6. This is for theta equals to 5 pi over 6, radius 1 to 3. So the region we are talking about is this. But not including the lines part. So if I use, let's say, a very thick blue line, so it should be this part here. This will be dashes, and including the arc. You see what I mean? Including the arc. Because the radius is including 1 and including 3, right? But not including the segment here. Okay, now that's for the region, the easy region. But how about going back to common graphs? How about going back to the common graph or common equation? So we already have first one when r equals to constant. That's a circle. Second, when theta equals to constant, that's a line through the origin. Line through origin. What happens if we have x equals to constant? And later on when y equals to constant. Let's try to develop it. So for example, when x equals to, let's say, -2, what will the polar equation be? X is r cosine theta equals to -2. So r equals to -2 secant theta. Now we usually describe a polar equation as r as a function of theta. Okay, we want to isolate the r as a function of theta. Now you will see when y equals to constant, then you will have cosecant. Y equals to, let's say, 3, r sine theta equals to 3, so r equals to 3 cosecant theta. Okay, more. How about r equals to k times cosine theta? Now you will see this is a circle centered at k over 2 comma 0, that's on x-axis, with radius k over 2. Now let's see, for example, r equals to, let's say, 6 cosine theta. I was planning to go a bit faster on this 10.3. Apparently today, if I want to give more details, we may have some big issue. I need to slow down to teach you how to graph. So r equals to 6 cosine theta. I will multiply by r both sides. Not squaring both sides, no, I multiply by r both sides. The purpose is so that on the left-hand side, I get x squared plus y squared, and on the right-hand side, I get 6x. I move the 6x to the other side. And then complete the square. You see that 9 actually comes from the square of half of that 6. Is 6 here, right? That's 6 there. You divide by 2. That's how you get that 3. And then you square the 3, you get that 9. Okay? Then you see on the left-hand side, we get x minus 3 squared plus y squared equals to 3 squared. This is a circle centered at 3, 0 with radius 3. Now you will see this kind of graph always touch origin. Okay, the center is 3, 0, and the radius is 3 because it touched the origin. Okay. Now, before I go on further, I would like to say a note. A note, and this note is important. If r theta depends on cosine theta or any exponent of that only, no sine theta, okay, then the graph has x-axis symmetry. Why? Depends on cosine theta. You will see that when you go in the theta direction and when you go to the negative theta direction, it will give you the same x. If you go to theta direction and negative theta direction, it will give you the same x opposite wise. Now that tells you that we have x-axis symmetry. Okay. In fact, we can go further using this observation. If r theta depends on sine theta only, then the graph has quote-unquote y-axis symmetry. Actually, we can observe that already here. Notice that x equals constant, right? X equals constant, x equals to negative 2 is like this, right? This is the y-axis. Okay. Now, it depends on cosine only, right? Negative 2 over cosine theta. And notice that it has x-axis symmetry. Now, for y equals to constant, it has y-axis symmetry, and the r depends on sine only. Right? This is 3 over sine theta. Right? It depends on sine only. Now, if you have the mixture between sine and cosine, then you may not have that privilege of x or y-axis symmetry. Okay. Going back to this important graph. Therefore, you will see r equals to k sine theta will give us a circle centered at k 0, k over 2 with radius k over 2. So it will pass the origin also. Let's say, for example, how do we play with the equation first? Okay, let's say r equals to, let's say, negative 6 sine theta multiplied by r both sides, such that I get x squared plus y squared equals to negative 6y, x squared plus y squared plus 6y equals to 0. This is x squared plus y squared plus 6y. What do I need to add by the way to complete the square? Add by 9, that's right. So I add 9 here, I add 9 here, I will add x squared plus y plus 3 squared equals to 3 squared. That's a circle centered at 0, -3 with radius 3. Pictorially, it looks like this. Yeah, pictorially, it looks like this. So this is -3. The radius is 3. Okay, but I'm not really happy with that. Let's do a polar graphing. What I don't want to happen is you know so much about polar equation, polar integration, polar this, polar that, but you can't even graph it. That's so sad. Okay, so polar graphing, let me see. Can we graph this on the polar coordinate system instead of simply the rectangular one? In other words, we want to get the same graph like this. Okay, we want to say get the same graph like that here. Now let's point out first the radius. So this is radius 1, 2, 3, 4, 5, 6, 7, 8. So later on, our circle is supposed to be something looks like approximately like this. It's not wide enough. Approximately like this. Okay, that's what it's supposed to look like. Now, I want you to graph this. Can you graph polar? Have you ever graphed polar coordinate system? Polar graph, polar equation. Let me use blue. Okay, so what you can do is you create a table. This is the theta. This is the r, which is -6 sine theta. Okay, now we know because this graph, this function depends on sine theta only, then the graph will be symmetric with respect to y-axis. So what you can do, you find the graph in the first quadrant and -1, quadrant 1 and quadrant -1. Because whatever you get here, you will copy paste to that side. Okay, so with that said, then I will get the theta. Let's use special angle. I will get the theta. Of course, I use 0, pi over 6, pi over 4, pi over 3, pi over 2, and also negative pi over 6, negative pi over 4, negative pi over 3, negative pi over 2. Now, can you use, or you can also use degrees, even though I prefer you to use, it's supposed to be in radian, not in degrees. Okay, but if you want to do the graphing fast, you may want to just use the degree then. So this one here, the r will be 0. This is r equals to -3. This is r equals to -3 radical 2. This is r equals to -3 radical 3. And this is -6. The first coordinate, 0, 0. coordinates here. Second coordinate, pi over 6, but I shoot backward -3. Pi over 4, this is pi over 4, but I shoot backward -3 radical 2. What is -3 radical 2 in decimal? 4.24. That is 4.24, approximately 4.25. How about 3 radical 3? Approximately 5.2, 5.2. At pi over 2, at angle pi over 2, I shoot backwards 6 units. I shoot backwards 6 units, it gives me this. Now, if you want to make it even finer, then you try to find out what's the radius when the theta is pi over 12. Okay, but well, you can do it yourself. And then when theta is -pi over 6, so it is in this direction later on. When theta is -pi over 6, we get, oh, I wonder what we get. We get r equals to -6 sine -pi over 6. That's positive 6 times 1/2. That's 3. Oh, okay. So at -pi over 6, I go 3 units in the same direction. And then I believe that would be 4.24, 5.2. If you want to make it even finer, again, you see what happened at pi over 12 and the rest. But I think, let's see, 15 degrees. -6 sine 15. I get -1.55, 1.5, approximately 1.6. So approximately here. So when I try to graph that, it will look like this. But, let me cheat. Things to become. Okay. Oh, you see, it happens to hit all 6 of them. Actually, all 8 of them. And notice that I just realized that when I graph this one here, reflecting that to the other side of y-axis give me this part. That makes me suspect of one thing, that it will travel this one circle only with pi instead of 2 pi. Think about it. Okay, what I want to say is the following. When 0, pi over 6, pi over 4, pi over 3, pi over 2. Okay, and then using that direction, you will see that we have 2 pi over 3, 3 pi over 4, 5 pi over 6 pi. So only with period of pi, you already make one circle. You don't need 2 pi to make this one circle. Okay, now then next, a more important family of curves is the group of they call that cardioid. Do they call that cardioid? Let me check. This one, the group of cardioid family of cardioid or cardioid? Question mark here. Correction. Not our textbook don't call that cardioid. Lima Shong. It has this pattern. R as a function of theta is A plus B sine or cosine theta. You will see that this guy here has y-axis symmetry because it depends on sine theta only. And the one here has x-axis symmetry because it depends on cosine theta only. I mean, the rest are constant. I will graph 3 equations, and then I will use my software to sharpen our intuition. Okay, I will start with, for example, R equals to, let's say, 5 plus 3 sine theta. Because it is symmetric with respect to y-axis, then let me ask you to construct the table for now. For theta, 0 degrees, 15 degrees, 30 degrees, 45 degrees, 60 degrees, 75 degrees, 90 degrees. That's in the first quadrant, and in quadrant 4, because it's symmetric with respect to the y-axis, right? Symmetric with respect to the y-axis. So I would just do quadrant 1 and quadrant 4. In quadrant 4, that will be 270 degrees, 285 degrees, the 15 degrees correspondence, 300 degrees, 315 degrees, 330 degrees, 345 degrees. Now, what I want you to do is to find the values for all of this. Can you do that? You can use your calculator if you want. I mean, but I think what I will do, I use my Excel. I just don't know if my Excel is in degrees or in radian. Give me a sec. Yeah, you do that. I do that too. Okay, you do that. I do that too. So this is my theta. This is my R. Do I want to make it in pi or in degrees? I think I make it in degrees. I think I will do it in degrees. Give me a second. I have too many files open. Start button. Oh, I'm still here. Okay, let me make it here. I'm in Excel right now. You can use your calculator if you want. 0, 15, 90, and then 270, 285, I can go to 360, and this is equals to 5 plus 3 times sine of this guy. Now the thing is, I'm not sure if let's get some help. Function sine. The angle is in gradient. So multiply by pi over 180. Okay, then that's equals to this guy times pi over 180. Now I need to have 5 plus 80 times. Now copy paste. Round it to 2 decimal places, or actually only 1 is necessary. Round to 1 decimal place. So if you really know how to use Excel, this can be quite useful. This can be quite useful. Okay. I program from my Excel. So you see what I do there, right? Okay, going back to this guy. So I don't need this. Not needed anymore. You know what? Let me play with it. Remove the whole thing here. Down here. Okay. And then why do you do that, Thomas? Because I want to polar coding. Enlarge to 100%. Enjoy. Okay, draw from when theta equals to 0, it's 5. 1, 2, 3, 4, 5. It's here. 15 degrees, 5.8. 30 degrees, 6.5. 45 degrees, 7.1. 60 degrees, 7.6. 75 degrees, 7.9. 90 degrees is 8. At 270 degrees, it's 2. 285 degrees, 2.1. So it just increased a very little bit. 300 degrees, 2.4. 315 degrees, 2.9. 330 degrees, 3.5. 345 degrees, 4.2. So it looks like approximately like this. That's what it looks like. Now then copy paste that to the left. So you reflect whatever graph I have on the right hand side now. Copy paste that to the left. So that's 7.9, 7.6 approximately here. 7.1 is approximately here. 6.5, 5.8, 5. And then 4.2, 3.5, 2.9, 2.4, 2.1. Because we know it will be symmetric with respect to the y-axis. Now notice that if we look back into, I have a chat coming in, would we have to graph on the test? I did ask that one time in the past. I did ask that one time, as I remember. I did one time. But then students consider that actually a bonus question because they know what to do. Okay. Now, let's come back here. Notice that the R, if you think about this, the R can never be negative because the maximum for this, the maximum, let me use red color, the maximum is 8. And it happens at theta equals to pi over 2. Minimum at 2, it happens at 3 pi over 2 or 270 degrees. Okay, so when somebody asks me to graph this, I know, oh, it follows the Limachon pattern, A plus B sine theta, right? So it is a Limachon pattern, and I want to know what it will look like. Oh, it's sine theta, so it must be symmetric with respect to the y-axis. When theta equals to 0, that's 5. When theta equals to 90 degrees, that's 8. When theta equals to pi, that's 5 again. When theta equals to 270 degrees, that's 2. So I see, oh, you know what? It will approximate like this. Okay. Now, it becomes cardioid. It becomes cardioid. I still don't know if it is cardioid or cardoid. Let's see. I don't see any reference for that here. We have cardioid if the constant and the coefficients are equal. So let's say if I have r equals to 4 plus 4 sine theta. Now, notice that the maximum happens at 8 when theta equals to 90 degrees. The minimum is 0 when theta equals to 270 degrees. Pictorially, it would be 4, 8, 4, 0. Like that. We say it's cardioid because it looks like a card. It looks like a heart. It may be sharp here, though. It may be sharp here. Okay, we will do that kind of analysis later on. But notice that if the coefficient and constant have the same number, then it will touch origin. Okay, it will touch origin. If the coefficient is smaller than the constant, then it will not touch origin. It will never be 0. Right? Now, of course, then what happens if the coefficient is larger? Let's say 3 plus 5 sine theta. Now you will see it actually looks like 3 here, 8 there, 3 here, but then negative 2. So it looks like the following. It goes this way. There must be a theta where it actually crosses the origin and make a small loop. Like that. Okay. Let's see what the graph looks like. So the first one, r equals to 5 plus 3 sine theta. That's what it looks like. That's what we had earlier. Okay. Now let's change that. Becomes the same 4 plus 4 sine theta. That's what it looks like. It goes through the origin. Right? Should I screenshot this? Let me screenshot that and put it at download. Give me a second. Let's screenshot this. Put it at download. The one we had earlier was 5 here, and then 3 here. And then the last one is when the coefficient is greater than so in reality though, when we need to do analysis, you just need the sketch of that. You just need to know, oh, what it looks like. Okay, not precisely. The detail will come after. Okay, the detail will come after. So these are the three graphs we did earlier. Now, what I will do next is I will do the analysis on this 4 plus 4 sine theta. Oh, it's cardioid. I found it. Yeah, cardioid. Cardioid. Comes from the word cardio, which means heart. Okay, heart is when the one it doesn't have a loop. So this is cardioid. Okay, now this is Limachon without loop. This is Limachon with loop. Am I going back to that? Oh, I'm sorry. I'm sorry. Here. So this is cardioid. This guy here is Limachon without loop. This Limachon with loop. We will also work on the tangent line. Oh, you know what? Distance between points first, because that's easy. I should have done it. No, I do it later then. Tangent. Tangent line. We will do dy dx using theta as our parameter. So we will have, this is dy d theta over dx d theta. Now we know y equals to r cosine, r sine theta. So dy d theta will be dr d theta sine theta plus r times cosine theta. While dx is r cosine theta, so dx d theta equals to dr d theta cosine theta plus minus r sine theta. And the way it works is the same to what we did with parametric equation. The horizontal tangent line, dy d theta equals to 0, but dx d theta is not, and so on and so forth. Okay, so with that said, let's take a look on deeper look into this. For example, let r equals to 4 plus 4 sine theta. Now we have known that the graph looks like this. This is what the graph looks like. I wonder if I can put this. This is what the graph looks like. Copy that downstairs. Now the thing is, from here we see that it has horizontal line at theta equals to pi over 2. Right? It has horizontal tangent line at theta equals to pi over 2. It has vertical tangent line at some angle here, we don't know. We need to look for it. Okay. The thing is, when I try to graph it this way, it's way too rough such that there's a big possibility I get my angle wrong. So the only way is actually doing it by computation. Okay. Oh, we have two more horizontal tangent lines at two different theta here. Okay. So those quote-unquote critical coordinates, this one, that one is clear, pi over 2. This angle here, I don't know. This is something, comma, what angle theta unknown. You see what I mean? We don't know yet. Theta equals to what? This one, theta equals to what? This one is easy. This is theta equals to pi over 2, right? Okay, theta equals to what? Theta equals to what? That's what we want to do, okay? And actually, there's one more thing here. We will have issue here later on. You see what I mean? We'll have issue there. At theta equals to 3 pi over 2, we will have issue. Is it a vertical tangent line or horizontal tangent line, or just happen to be neither one? Okay, so let's go. R equals to 4 plus 4 sine theta. So dr d theta equals to 4 cosine theta. Then dy d theta equals to, let me write it down first, dy dr d theta, dr d theta sine theta plus r cosine theta. This is 4 cosine theta sine theta plus 4 plus 4 sine theta cosine theta. That is equal to 4 common factor cosine theta, and I add another one sine. There will be 1 plus 2 sine theta. Is it right? A common factor 4. Common factor 4 going out. Another common factor cosine going out. Do you see that? Okay, so I basically add 1 plus sine theta plus sine theta, right? Well, you can distribute that first and then factors. Now, this is equal to 0. If you set it equals to 0, when you set it equals to 0, you get cosine theta equals to pi over 2. I'm sorry, cosine theta equals to 0. Therefore, theta equals to pi over 2 and 3 pi over 2. And write it separately. Write it like this. I hate it very much when somebody write it this way. I mean, come on, can you be any lazier? Oh, separate them. But Thomas, that's the way the textbook write it. Then you write a textbook then. Now separate them, okay? Because we need to analyze that further. Separate them, okay? Here we have sine theta equals to -1/2. So theta should be in quadrant 2 and quadrant 3 and quadrant 4. Sine is negative, okay? That would be theta equals to 7 pi over 6 and 11 pi over 6. But no, we cannot say that we have horizontal tangent line at this theta yet. No, not yet, not yet. Why? Because we need to make sure that dx d theta is not 0 at those theta. Okay, so let's take a look on what happened with dx d theta. Dx d theta is dr d theta cosine theta minus r sine. That is 4 cosine times cosine theta minus 4 plus 4 sine theta. 4 plus 4 sine theta times sine theta. We have 4 negative 4 sine theta plus 4 times cosine squared theta minus sine squared theta. That is, this is plus 4 cosine 2 theta. Now I will set this equals to 0. So that basically I do dx d theta to be 0. I end up having cosine 2 theta equals to sine theta. Do you know how to solve this? It's 1 minus 2 sine squared theta equals to sine theta. Okay, so 0 equals to 2 sine squared theta plus sine theta minus 1. And then we factor it. So sine theta equals to 1/2, or sine theta equals to -1. Oh, hold on. Sine theta equals to -1 means theta is negative, or is 3 pi over 2. So 3 pi over 2 give us dx dy 0. And I mean dy d theta 0 and dx d theta also 0. Theta equals to pi over 6. Theta equals to 5 pi over 6. In other words, dy d theta equals to 0 when theta equals to pi over 2, theta equals to 3 pi over 2, theta equals to 7 pi over 6, theta equals to 11 pi over 6, while dx d theta equals to 0 when theta equals to pi over 6, theta equals to 5 pi over 6, theta equals to 3 pi over. So we are okay on this guy, this guy, this guy, this guy, this guy. When dy d theta is 0, the dx d theta is not. When dx d theta equals to 0, the dy d theta is not. We have issue here. Okay, at least at this point we can say the following. We can at least at this point we can say the following: horizontal tangent line at theta equals to pi over 2, theta equals to 7 pi over 6, theta equals to 11 pi over 6. If I look back to that graph here, this is one of my horizontal, okay, and the other two are actually here. Now I can tell more about this. This is 7 pi over 6. This is 11 pi of 6. Okay, as we predicted earlier, we have issue at 3 pi over 2. Right, remember that? We have issue at 3 pi over 2. We don't know if that's vertical or horizontal or nothing. Now, from here, we also see that we have vertical tangent line at theta equals to pi over 6, theta equals to 5 pi over 6. Pi over 6. When we say pi over 6, it refers to this angle here. This angle here is 30 degrees. Okay, that angle there is 30 degrees. And this is 5 pi over 6. And what happened with at theta equals to 3 pi over 2? Then we need to do separate analysis. At 3 pi over 2, dy d theta equals to dx d theta equals to 0. So that's undetermined, right? What we will do is then we do limit condition, limit theta approaching 3 pi over 2 of 4 cosine 4 cosine theta 1 plus 2. Maybe I do it this way. Sorry, I try to rush. Dy d theta over dx d theta, so that you know what I'm doing, right? This is equal to limit theta going to 3 pi over 2 of 4 cosine theta 1 plus sine 1 plus 2 sine theta, while on the denominator we have negative 4 sine theta plus 4 cosine theta, negative 4 sine theta plus 4 cosine 2 theta. Oh, I can cancel the 4 at least. So limit theta going to 3 pi over 2 cosine theta times 1 plus 2 sine theta. I really hope I can cancel something though. If I cancel the 4, then I will get cosine 2 theta minus sine theta. Should not help me. Oh, you know what? We may be able to do this. Limit theta goes to 3 pi over 2. On the top, I get cosine theta plus 2 cosine sine. That's sine 2 theta. Over negative sine theta plus cosine 2 theta. Now when I plug in theta equals to 0, theta equals to 3 pi over 2, I get 0 over 0. Then let's try doing L'Hopital. I will get sine, negative sine theta. I don't think we go anywhere from here. I don't think we go anywhere from here. This is 2 cosine theta. While this one is negative cosine theta minus 2 sine theta. wonder if it works. It doesn't give me anything. Let's see. Just scratch work. This will give me what, negative of negative 1 1 plus cosine 3 theta is negative 1, so this is minus 2 over this one is minus 0. This is 0. Right? It gives me something over 0. It gives me something over 0. I don't like that. But at least it's something over 0. See, so something over 0, either it's positive infinity or negative infinity. That's all right. So let's do it this way then. Limit theta going to 3 pi over 2 from the left hand side of that 2 cosine 2 theta minus sine theta over negative 2 sine 2 theta minus cosine theta. And see what happens if you approach that from the left hand side. And you also see what happens if you approach that from the right hand side of 3 pi over 2. And you plug in 3 pi over 2 here. And I plug in 3 pi cosine 3 pi negative. It's negative 2. Minus negative 1. But the denominator is the crucial one. I think this will give us 0, but from the positive side, is it negative 2 sine 3 pi from the left hand side, slightly more than 3 pi. That's positive. So that's negative 2, that's negative here. Minus, how about cosine 3 pi over 2 from the negative side? That's also negative. Let's see. Oh, it's minus though. Maybe I do it this way. I factor the negative out. No, I still don't get it. I don't like this. You know what? I may need to get some break. Let me take a break. Too much detail here. That's the thing. Too much detail here. I wonder if I can actually make it nicer somewhere here. You know what? Let me play around here. Take your break. Let me give you a break. Also recording. So what I did was I tried to find dy dx. I tried to find dy dx, and it turns out after doing some algebra and then L'Hopital rule, I found that if I approach that from less than 3 pi over 2, I get infinity. When I go from greater than 3 pi over 2, I get negative infinity. Now, if I see this kind of case, I rather than take a look on the dx dy instead. Okay, basically you do the reciprocal, and the reciprocal of infinity is 0. The reciprocal of negative infinity, as you will see, also equals to 0. So instead of going through the one I did in black color, you may consider doing it the one with red color. But that's if on your scratch paper you find out that you get infinity and negative infinity. Okay, so if we look back here, we have issue here earlier. Our issue was, do we have vertical tangent line or horizontal tangent line at this point? Or is the tangent line not equal at all? Like this, like this. This is what I want to say. You see, if I erase all of this here, okay, from what we see, it seems like the tangent line here is going this way, and the tangent line, if you approach this way, is that. So they are not equal at all. Okay, so as if we are saying there is no tangent line at 3 pi over 2, right? But if we zoom that in later on, you will see that it actually looks like this. Instead of like cornering, it's actually sharpening. Now let's take a look at change this to 4. Change this to 4. I will super zoom this. I want to see what happened there. You see that it's actually, if you super zoom that, it actually becomes really sharp, right? Okay, so the slope when you approach from slightly less than 3 pi over 2, the slope becomes infinity, while if you approach from slightly greater than 3 pi over 2, the slope becomes negative infinity. Or, to be more precise, the dx dy eventually becomes 0. See? It basically becomes a vertical line eventually. Okay. Now, this is the way we treat the situation when we get dy d theta and dx d theta equals to 0. So our analysis earlier, based on what we see, we thought that the tangent line from this side will go only this way, and from this side it goes that way, and therefore the limit does not exist, right? It turns out that the limit actually exists. The limit actually exists. Visually it's not, but the limit actually exists, and it is dx dy is actually 0. Therefore, it is a vertical tangent line instead. It's a vertical tangent line instead. So here it will be a vertical tangent line instead. But the graph seems to be deceiving though, as if it looks like this, right? Give us a corner, but no, it's actually giving us a needle instead of a corner. Okay, well, that's one analysis for this graph. What else? Let's see some other family of graphs. Well, the reason I want to go over this because you would see this a lot in your calculus 3 later on. What happens if I have, for example, double angle? Oh, we have not done cosine now. Oh, if I change this sine becomes cosine, that's what it looks like. Okay, let me screenshot this and put it in our so later on when you look at your notes, we have some graph we look into. How about double angle? How about sine 2 theta? Now, sine 2 theta, this function here depends on sine. Okay, with double angle. So we know this will be symmetric with respect to y-axis. Oops, too small. Let's enlarge the radius. Radius 5. But Thomas, why is it that we see the graph is actually not only symmetric with respect to to y-axis, it also symmetric with respect to x-axis? How do we explain that, Thomas? I don't know. Honestly, I don't know. I don't know how to explain that. I know that it's symmetric with respect to y-axis. And as we expect, it will be also the same case if I make it 3 here. Right? It is symmetric with respect to y-axis. And the strange thing is, if the coefficient of the angle is odd, then the number of leaves you have will be odd. See? Take the picture. Collection. See, if I change this to 3, then I will have 3 leaves. Right? Yet, if I make it into even, say 2 here, I have double leaves. The number of leaves is double. So we learned about phenomena here. Okay? See, if the coefficient of the angle is 4, you will end up with 8 leaves. Now notice that because it depends on sign, then all of the graph will be symmetric with respect to y-axis. Let's change this to cosine. If it is cosine, then it should be symmetric with respect to x-axis. The number of leaves will be equal to the coefficient if it is odd. If it is even, then the number of leaves will be double. And yes, the principle that it is symmetric with respect to x-axis because it depends on cosine still be maintained. But Thomas, for cosine 4 theta, seems like it also have symmetric with respect to y-axis. Why is it that when the coefficient is even, we have that phenomenon? Why is it that when the coefficient is even, it becomes symmetric with respect to x and y-axis, but when the coefficient is odd, then you have only one symmetry? Honestly, I don't know. But I think it's because, let me go back to your notes. I think it is because that we can rewrite, it must be because we can rewrite this sine 2 theta, for example, in terms of cosine. In terms of cosine. So let's say this is equals to the 6 times, what's that? That's sine squared. So this is 6 times 2 times sine theta cosine theta. I try to rewrite it in terms of cosine only. Yeah, maybe because of that. Maybe because of that. Okay, for the odd ones, no, this is only symmetric with respect to y, not x. When it is even, x and y. Even, x and y. And it also the same case with cosine. When it is odd, the number of leaves is the same, and it only have x-axis symmetry. But when the cosine is have even coefficient, then the number of leaves is double the coefficient, and it has the x and y-axis symmetry. If you remember from pre-calculus, if a function, actually I should not say a function, if an equation have x symmetry, x-axis symmetry, and y-axis symmetry, then it must have origin symmetry. Do you know that? Do you realize that? In other words, you can rotate this graph 180 degrees. You can rotate this flower 180 degrees and it still match. Okay? In this case, actually, you can rotate that every 45 degree, it will match. Okay? The last part that I need to cover from this section is distance between 2 points. The distance between two points in pole. Suppose this is my pole, and we have two coordinates. Let's say this one is r1 theta 1, and this coordinate is r2 theta 2. The question is, what is the distance between these two coordinates? Actually, the idea is quite simple. We will use law of cosine, in which the angle here is theta 2 minus theta 1. Okay, the angle here is theta 2 minus theta 1. Now then the distance here, the distance squared equals to r1 squared plus r2 squared minus r1 r2 cosine theta 2 minus theta. Cosine included angle. Okay, use law of cosine. So suppose, for example, we have that question number 13. Find the distance between 2 comma pi over 3 in polar and 4 comma 2 pi over 3 polar. Distance squared will be equals to the first radius squared plus the second radius squared minus the product of the radii times cosine of the difference of the angle. That is 4 plus 16 minus 8 cosine pi over. So that will be 20 minus 8 times 1 half. That's 16. So the distance is 4. Okay, let me close this here and we suggested homework from this 10.3. I would like you to do number 7 to number 25. And then try number 29, 31, 39. Others are not so important, so I guess. Oh, you know what? Number 33 is also quite interesting. For number 33, you will see that's actually a spiral. R equals to theta. Now notice that this theta is in radian. Okay, so when theta equals to 0, it's here. 45 degree is pi over 4 is here. And then later on pi over 2. And then pi. So eventually you will see it becomes a spiral. I believe I already uploaded my new card on the file folder. So you can use that actually to graph. Okay, now 10.4. This section tends to be on the easy side. 10.4 is on area and length. First area and second length in polar. Part A, the areas. Suppose I have a curve like that. Let's say this is r theta. Okay, and I want to find the area between these two sectors here. Let's say I want to find the area between these two sectors. Now, if I supersum this, eventually this becomes straight. Okay? Eventually, if I supersum this, then it eventually becomes like this. It becomes a sector if I supersum that. And the area of the sector will be, if you remember the sector area of a segment. If this is theta, this is r, the area equals to 1/2 theta r. Okay, so if this is the radius r as a function of theta, and this is a very small change of angle, they call it d theta. So the area here, the differential of the area is equals to 1/2 r d theta. I'm sorry, theta r squared. I wonder if you remember this. Do you remember this formula? Do you remember that formula? No? Area of a segment. Yeah, area of a sector. Okay, let's do it. Proof. So I will prove this here. Area of a circle is 2 pi r. What am I doing? Pi r squared. Pi r squared. Okay, now the sector area is proportional to the central angle. Okay, so area of the sector over pi r squared equals to theta over 2 pi. So the area of a sector equals to theta times pi r squared over 2 pi. Now you see the pi cancels, right? Area of that sector is therefore 1/2 theta r squared. Okay, now in this supersum region, I replace the theta by d theta. So the differential of the segment area, sector area, is 1/2 r squared d theta. Therefore, the area equals to 1/2 integral r squared d theta. Okay, from theta equals to, let's say, alpha to theta equals to beta. Of course, the r here is a function of theta. Now, with that said, let's do problems right away. That's the formula, right? Box it. Problems number, let's see, problem number 2. Find the region. Find area bounded by r equals to cosine theta, where the theta is from 0 to pi over 6. R equals to cosine theta means the center is 1/2, 0, with radius 1/2. Now what I need is from 0 to pi over 6. And this part. What is the area there? Then the area equals to 1/2 integral from 0 to pi over 6 radius squared cosine squared theta d theta. This is equal to 1/2 times 1/2 integral from 0 to pi over 6 of 1 plus cosine 2 theta theta. That's 1/4 theta plus 1/2 sine 2 theta from 0 to pi over 6. That's 1/4 pi over 6 plus 1/2 sine pi over. That's pi over 24 plus radical 3 over 16. How about number 6? They tell us that r equals to 1 plus cosine theta, and we want the angle from the graph. The graph looks like this. The graph looks like this. It's a RDOE. But what you need is only the ones in quadrant 1 and quadrant 2. Okay, so from there we see that the angle from theta equals to 0 to theta equals to pi, right? So the area equals to 1/2 integral from 0 to pi of 1 plus cosine theta squared d theta. That is equals to 1/2 integral 0 to pi 1 plus 2 cosine theta plus cosine squared theta d theta. That's 1/2. I want to claim that this will be 0. Do you know why? The graph of cosine, in the first and second quadrant. In the first quadrant is positive 1. The area in the second quadrant is negative 1. Okay, so if you go from 0 to pi, the area will be 0. Right? Okay, and the area of a constant will be basically the constant 1 multiplied by the arc length, by interval, the length of the interval. So this will be 1/2 pi plus 1/2 integral from 0 to pi of cosine squared theta. For the same reason, you will see that this is That's going to be 0. And that will be pi of 4. In total, the area will be 3 pi of. How about number 8? They give us the picture. That's why I want to take advantage of. They give us the picture. Oh, let me go with that. I think I have another. Number 8. The graph looks like this. It actually goes this way. Okay, now the question is, find the area of only one leaf. Now that one leaf we start from, theta at the origin, going to back to theta in the origin. So we will be looking for two consecutive thetas that reach the origin. Okay, we'll be looking for two consecutive thetas that reach the origin. This is r equals to sine 2 theta. When I set it to 0, then 2 theta equals to multiple of pi. Right? Multiple of pi. Now divide by 2. Actually, is it pi? Yeah, that's right. Divide by 2, then it will be k pi over 2. Somehow I don't think it's true. So theta equals to 0 and theta equals to it looks like this series here. So it will be 0, pi over 2, pi, 3 pi over 2, and on. So for one leaf, area of one leaf will be 1/2 integral from 0 to pi over 2 of sine square 2 theta d theta. That's equals to 1/2 times 1/2 integral 0 to pi over 2 1 minus cosine 4 theta. Yeah, but the period of cosine 4 theta is pi over 2. So the area for this term of that integral will be 0. The final answer, I get pi over 8. That's for number 8. How about number 12? Somehow think I get a bit bored with this because I keep on just applying the formula. Okay, that's 4 plus 3 sine theta. We want to find the area that it encloses. This is symmetric with respect to y-axis. When theta is 0, this is 4, this is 7, this is 4, this is negative. This is radius 1. So it looks like this. No, it's not. It's supposed to be symmetric with respect to y-axis. Okay, because it is supposed to be symmetric with respect to y-axis, so the area equals to 2 times 1/2 integral from negative pi over 2 to pi over 2 of 4 plus 3 sine theta squared d theta. That's equals to integral from negative pi over 2 to pi over 2, 16 plus 24 sine theta plus 9 sine squared theta d theta. Sine in quadrant, sine graph looks like this. Quadrant -1 and quadrant 1 will cancel. So this guy will go to 0. Boom. Okay, the first term will have 16 pi. Right? Okay, and then plus 9 times integral negative pi over 2 to pi over 2 sine squared. That's 1 minus cosine square 2 theta d theta. But I know the period of cosine 2 theta is pi, and this length here is already pi, so that will also be 0. You see, I save a lot of time by knowing what the by knowing the graph, and therefore the integral 9 times the length of the integral. So the total is 25 pi. Number 18 will be quite challenging. Number 18, I don't even know what this would be. Suppose I ask you this question, then how will you do it without graphing calculator? Thomas, how will you do it? Okay, let's try. This actually means two things. First one, that r will be plus minus square root of sine 2 theta, right? Okay, and sine 2 theta has to be positive or 0. Which means, okay, let's see the critical value, critical numbers. Sine 2 theta equals to 0, and 2 theta equals to k pi. Theta equals to k times pi 2, the sine graph 0, pi 0, pi and 1. In the first quadrant, that's positive, negative, positive. Okay, I think it gives me some idea. And because it depends on sign, then it must be symmetric with respect to y-axis, right? And it must be symmetric with respect to y-axis. Actually, on the top of that, because the radius is plus minus, then it will be symmetric with respect to origin. Okay, so when this is 0 to pi, it looks like this, but it also have the negative counterpart. From pi over 2 to pi, there should not be anything there. From pi to 3 pi over 2, you have something looks like this, a loop and the negative counterpart. So yeah, that's what it looks like. So it will just look like a diagonal 8. Let's confirm. Let's confirm. So r squared equals to sine. It's so cute. That's what it looks like. And what we need is only the area of one loop. One loop, right? Okay, so at least I get the sketch. So the area of one loop, going back to the graphing, the area of one loop is 1/2 integral from 0 to pi over 2 of r squared. But our r squared is sine 2 theta. Sine 2 theta. Not 2 pi, 2 theta. Theta. So this is 1/2 times 1/2 negative cosine 2 theta from 0 to pi of 2. That's 1/4 of -1, actually positive 1 minus -1. So the area is 1/2. Okay, that's for number 18. How about number 24? Find the area inside the first curve, which is r equals to 1 minus sine theta, and outside of the second curve, r equals to 1. Let's sketch that first. And r, when theta equals to 0, it's 1, 0, 1, 2. So it looks like this. But outside r equals to 1, so outside of the circle. So outside of the circle. Then you need to find the intersection of these two coordinates. At what theta they actually meet. But from what I see here, let's set them equals to first. Okay, solution. Let's find the intersection. That's how we find our integral later on will be from what theta to what theta. Okay, so sine theta equals to 0. Okay, theta equals to a pi. Now from the graph we can see that the region we want is this region here. Okay, so the area will be 1/2 integral from pi to 2 pi the area of the one outside 1 minus sine theta being squared minus the one inside. Okay, that will be 1/2 integral from pi to 2 pi subtract by 1. So I will end up with sine squared theta minus 2 sine theta theta. In quadrant 3 and 4 for sine, oh, that's negative. Oh, okay, this one. So this is equals to 1/2 integral pi to pi sine square theta d theta minus 1/2 times 2 integral pi to 2 pi sine theta d theta. Now the area for each one of this segment here is 1, 1, negative 1, negative 1. So the area here will be negative 2. Okay. That's negative 1 times negative. And I know this will eventually be 0. Okay, so fast forward, this will be 1/2 times 1/2 times pi plus 2. So that's 2 plus pi over. Now, the last example here requires you to know how to graph what the graph look like first. Okay, that way then you can see, oh, you know what, then I need this region, the one I shaped there. Okay. This is where I will stop. So I do only the first half of 10.4. On Wednesday, I will go on with the second half. Now, I would like you to start reading chapter 11 though. Please start reading chapter 11. Suggested homework from here. 4A, I would like you to do number 1 to number 11. And then number 17 to number 33. It should be good enough. Just do the other. Okay, that's today.